Good morning, everybody. I will just quickly share my screen. And then hopefully I will put this on to slideshow from the beginning. Cool. So this morning I'm going to be talking to you about novel semiconductor heterostructures for green photonics. As Dimitra mentioned in this morning's opening talk, sustainability and energy efficient development is really important for the future of networks with the amount of energy that we currently use within telecommunications and the internet. A good example of this, so I'm originally from New Zealand. I moved over here in 2019 to do my PhD. Before I moved over here, I was working at Vodafone New Zealand in the optical engineering space. Now, the growth of the internet, I think, can be really captured by the deployments that we were doing in that time. In 2017, I was in the team that deployed 400 gigabit per wavelength per second speeds across New Zealand. And 3 years later in 2020, obviously after I left the company and started my PhD, they then rolled out 800 gigabit per wavelength per second speeds across the country. So that's a 100% increase in traffic across the country in 3 years. So as we can see, the internet is growing exponentially, and as the internet grows exponentially, the energy that the internet is consuming is also growing at that same speed. And that's something we really need to be aware of and address going forward. So how do we do this? One option is when we look at the semiconductor lasers. So current commercial indium phosphide based lasers have pretty high wall efficiencies when we're looking at, the lower 918 nanometer wavelengths. However, when we get into the commercial in mid-infrared wavelengths that we use in datacoms and telecoms, which is the 1300 nanometer and 1550 nanometer, the wall plug efficiencies drop below 40%. Which is an incredible drop in the amount of power that's actually useful when it comes to how the internet's being used. So one of the big problems with this is that more than 50% of the carrier density at threshold is being used in Auger recombinations. So that's a big loss that we need to address. So we tend to have 4 losses when it comes to semiconductor lasers that we use in the telecommunication space, which is carrier leakage and reduced carrier confinement, reduction in optical confinement, Auger recombination, and intervalence band absorption. And they can sort of be demonstrated with our band structure in the figure to the right. So these are the four mechanisms that we need to address and try and fix when it comes to next generation semiconductor lasers for telecoms. So one of these options is what we call our novel heterostructures. So highly mismatched alloys, which are dilute nitrides and dilute bismuths and gallium arsenide, offer quite good pathways to suppress these losses. Dilute nitrides have improved carrier confinement because of the increase in the conduction band offset, and dilute bismuths have the option of suppressing Auger recombinations at 1550 if we can get above 10% bismuth in gallium arsenide. And they offer the potential to make uncooled long wavelength telecommunication lasers on gallium arsenide, which have high modulation speeds. So these are really promising pathways for energy efficient telecommunication lasers. And my research focuses on combining these two materials, so combining the dilute nitrides and the dilute bismuth layers into a type 2 heterostructure. And this could result in really strain balanced lasers that can have really promising threshold characteristics. They also are the structures that have the longest ever reported emissions on gallium arsenide, which is as we try and even exceed the 1550 nanometer, as we move into the hollow core fibers, the best wavelengths we use in hollow core fibers are actually above 2 micrometers. So, we need to be pushing that wavelength even further than 1550 we currently use for telecommunications. And also building on or growing on gallium arsenide have quite a lot of promise in terms of flexibility, because there's a possibility of monolithic integration of long wavelength optoelectronics, such as for VCSEL architecture. So there's some really promising pathways when it comes to integrating the highly mismatched dilute nitride and dilute bismuth into gallium arsenide based semiconductor lasers for uncooled telecommunications and long wavelength transmission going forward. So that's the end of my elevator pitch for today of my ongoing PhD research. I hope you found that interesting, and I shall pass over to the next speaker.
Okay, thank you very much, Zoe.